Hello everybody, this is the third video for chapter 5 of the statistical learning class. So this video will be a bit shorter than the others. So you can listen to it a bit quicker. So in this video we'll start with introducing the logistic regression approach. So let's compare this approach to the previous ones mentioned in the previous lecture. So in the previous lecture, we've introduced two parametric approaches for the classification, which were linear discriminant analysis and quadratic discriminant analysis. These two methods relied on the assumption that given observations are from a given class, their predictors are distributed according to a multivariate normal distribution. So logistic regression will be another parametric regression approach, but where the assumption about the distribution of predictors is not made anymore. So the logistic regression approach, although it's a classification method, we're going to see that it uses concepts of regression to perform the classification. Okay, so we will see how to turn a classification problem into a regression one. So for simplicity, in the course, we'll only illustrate the case where two classes exist. Okay, so we're going to assume there are two classes, 0 and 1. The case with more than two classes also exists and is developed in the literature, but due to the lack of time, we won't have time to cover the case with more than two classes. So we'll only consider the case with a single class or two classes. So for the logistic regression, we assume that there are two possible responses, which is the class is 1 or the class is 0. And for all observations within class 1, we're going to impose a response of 1, and for all observations in class 0, we're going to impose a response of 0. And this shows why we will be able to use regression concepts here. It's because although the classes are qualitative, we turn them into 0 and 1, which is quantitative. So for this reason, we now have quantitative responses, and thus regression methods will be shown to apply in this case. So we can use regression concepts we've used earlier to apply our classification approach. So basically, you can see the idea here is that if your predicted response is close to 1, then you can classify it as class 1. If your predicted response is close to 0, you can assign this observation or classify this observation as class 0. So to be more precise, the logistic regression uses the GLM regression model we've introduced in the previous chapter. So all the theory has already been worked out, so we won't repeat it here, but it's basically exactly the GLM regression model with a specific assumption about the distribution of the response and a specific link function. Okay, so as in GLM theory, we're going to assume that all data points are IID, independent and identically distributed. And then in the GLM model, we had to assume that given the predictors, the response is drawn from a distribution of the exponential family of distributions. Well, in this case, the response is either 0 or 1, so the assumption will be that the response is drawn from a Bernoulli distribution. And recall a Bernoulli distribution is worth 1 with probability p or 0 with probability 1 minus p. So here, this is the parametric assumption. It's a very simple distributional assumption, but here we see that instead of assuming a Gaussian distribution for predictors in the LDA or QDA approach, instead the distributional assumption we make here is that the response is Bernoulli distributed. And now about the link function. So in logistic regression, the link function that is used, we'll denote it here xi, and this xi, sorry, it's not xi, this one, I think it's phi, this one. So some variant of phi. I'll verify the symbol. I'll call it xi, but I'm sorry for that. I forgot the name of this Greek letter. Okay, so the logistic function that we're gonna use is the what we call the the link function we're gonna use is the inverse of the function xi here, which is the logistic function. So to be more precise here, in our model, the probability of being in class 1 given your predictors, this can be written as the conditional expectation of your response given your predictors, because the response is either 0 or 1. So the expectation of that Bernoulli variable is the probability that it's equal to 1. And here we're going to assume that this expectation is equal to this. So recall that in the GLM model, the expectation of the target or the response is the inverse link function applied to the linear combination of predictors. So this is what we're going to do here. But the inverse link function here, it's assumed to be the logistic function. Okay, so the logistic function, let's write it here. The logistic function here, this is exponential of x given 1 plus that exponential. So this quantity, it's a quantity between 0 and 1, which is desirable because applying this logistic function ensures that our probability for any for the response for any predictors is between 0 and 1, which is consistent with the probability. Okay, so because of that, the expected value of our target, if we use the logistic function as the inverse link function, is the logistic function applied to the linear combination of the predictors, and therefore it's exponential of the linear combination of predictors divided by 1 times that same exponential here. And now, why is there a tilde over the xi? It's because we augment the predictor set here by adding 1 in the first place so as to consider an intercept, such as we did earlier in the GLM chapter. Okay, so x tilde I contains 1 and all predictors, and the vector beta here is the column vector which contains beta 0, the intercept, and all slopes within the GLM model. Okay, so indeed using the logistic function ensures that for any values of beta and any predictors, the predicted expected target, which is the probability of being in the first class, is a quantity between 0 and 1, so this is a legitimate probability. So now what does the logistic function look like? I wanted to show a plot so you can see what it looks like. So once again, this is the logistic function. So if you plot this logistic function for various values of z, you see that the logistic function converges to 0 when z converges to minus infinity, and converges to 1 when z converges to infinity, and it increases like that. Okay, so it remains between 0 and 1, so it's consistent with the probability, and moreover, the variation is smooth and nice, so it's very convenient for modeling purposes. Okay, so now again, if we apply logistic regression, we need to have parameter estimates to determine the probabilities of being in each of the two classes for a given value of predictors. The great news is we've already explained how to obtain the parameters for a GLM model in chapter 4. So we won't repeat the theory here, but the approach pursued is maximum likelihood. Okay, so we said that GLMs can be estimated in many ways, but the traditional way for logistic regression is simply to apply maximum likelihood principles. Another good news is that if we apply maximum likelihood estimation with GLMs, then the asymptotic maximum likelihood theory explains how to obtain t-statistics and other test statistics which allow to assess the significance of each variable. Okay, so when we apply a logistic regression, we get t-statistics and we can determine from that p-values of the various variables and see which one are significant or not. Okay, so it's very close to a traditional regression model. Well, in fact, it is a traditional regression model. A lot of people use logistic regression in practice. It serves often as a benchmark within classification problems. Okay, so now once the betas from a logistic regression are estimated on the training set, what we'd like to do is to try to predict the class of a new observation in a test set. Okay, so if we have a new observation and its predictors are given by x0, the new observation is classified as follow. So its class is predicted to be the first class if, so y is equal to 1, if the estimated probability, so this estimated probability is basically the inverse link function applied to the linear combination of predictors, but the hat here means that we substitute the betas by their estimates. So this is our estimate of the probability. And if the estimate of the probability for a given value of predictors is greater or equal to 0.5, it means that it's more likely that, according to our estimates, that the value of the response is y is equal to 1. So we're going to classify it as y is equal to 1. Okay, first class. Conversely, if that probability is smaller than 0.5, we're going to classify it as second class, and by second class I mean y is equal to 0. So this is how we classify new observations within a linear regression. So we take the betas, we plug them into this expression, which is the inverse link function applied to the linear combination of predictors, where we use the predictors for the new observation, and this is how we get this. So this is with original predictors, but exactly as we did in chapter 4 or even chapter 3 with polynomial regression, we can take an original data set and design additional predictors which are transformations of the original predictors, so as to increase the flexibility of the model. Okay, so once again, if we have predictors x, well, we can take their powers, we can take trigonometric expressions of or transformations of these variables, etc., so as to obtain new predictors and to provide more flexibility within the model. So for example, you could have some form of polynomial logistic regression where, let's say you have a single original predictor x, then you can construct new predictors by considering like 1, x to the power 1, x to the power 2, x to the power 3, etc. until x to the power k. Okay, so if you do that, you could have a polynomial logistic regression where the estimated probability of being in the first class given your predictors x0 could be of the following form. So it's the logistic function applied to the linear combinations of the new predictors, where the new predictors are the powers of that original predictor. Okay, so the same concept of transforming predictors to get new ones and get a more flexible model still applies here. Okay, so now we want to compare the logistic regression to the previous methods we've introduced in this chapter. So more precisely, what we'll do, we'll compare logistic regression to linear discriminant analysis. Okay, so are the solutions to both methods similar? So is it worth exploring one instead of the other? What happens here? So we will outline here a very interesting relationship between linear discriminates and the logistic regression approach. Okay, so once again, we will illustrate this relationship or this link for the class of the case of two classes, so classes either 0 and 1, and we're going to illustrate it for a single predictor. Okay, however, this connection can still exists within a multidimensional setting when there's more than one predictor, but just to make the explanation simple, we will illustrate it for the case of a single predictor. So here let's denote, so there shouldn't be a D here, let's denote by P1x the probability, the true probability that the class is, the estimated probability based on our model that your observation is in the first class given its predictors are X. So one very interesting result here is the following. So the first result is that for the logistic regression, the log, so this expression, it's called the logit of P1. So the logit of the estimated probability of being in first class, given your predictor, univariate predictor is X in logistic regression, can be shown to be beta 0 plus beta 1x, where the betas are the ones directly obtained from the model, from the GLM model. Conversely, if you apply a linear discriminant analysis with a single predictor, it can be shown that the logit of the estimated probability of being in the first class is also a linear function of that predictor for some constants d0 and d1, which depend on estimated parameters within the LDA approach. So estimated values for the pi j's, the mu j's, and pi j's, mu j's, and the covariance matrix sigma. So the proof of this result is left for exercises. I highly encourage you to do it. So because of that result, you might say, well, these models, because the nature of the solution is exactly the same, probably they would provide pretty similar results in practice. So is that the case? Well, sometimes yes, sometimes no. Okay, so as we said, both methods imply that the logit of the estimated probability in first class is a linear function of the predictor. So because of that, in many cases, the solutions can be similar because their nature is similar, but sometimes both methods can lead to quite different classification rules. So why is that the case? It's because the constants beta 0 and beta 1 and d0 and d1, they're different here, and different approaches were used to obtain beta 0 and beta 1 versus d0 and d1. So the LDA approach relied on a Gaussian assumption of predictors, which is a pretty strong parametric assumption, whereas the logistic regression did not rely on such a more stringent assumption. It only assumed that the response was Bernoulli distributed. So because the underlying assumptions about the behavior or of the predictors or of the target are different, then the nature of the coefficients within that linear relationship differ, and therefore you might have very different values in practice. Okay, so this completes the discussion about logistic regression, which is a very, very, very well-known classification method, especially if you're in the case of two classes 0 and 1. Okay, now we'll switch to a completely different topic, which is the error rate. So throughout the chapter, we mentioned the objective function to minimize as being the out of sample error rate, but because we mentioned we should try to have an error rate out of sample that is as small as possible. But there is an issue with that objective function, which is that the error rate treats every type of misclassification equally. Okay, so misclassifying a class 1 observation into class 2 or misclassifying a class 2 observation into class 1 are penalized exactly in the same way. So for some problems that could be fine, but for some other problems this could be extremely problematic. So let's give an example, and these examples stem from cases where the cost associated with the different types of misclassification are asymmetric. So let's give the example of tumor detection. So let's say you have scans of various tumors, and from these scans you can extract some features of the tumors, and based on these features you'd like to determine if the tumors are either benign or malignant. So the idea here is that classifying a benign tumor as malignant is not so problematic, because if you do that you might do additional tests, and then these additional tests might lead to understand that ultimately the tumor is benign, so it's not really problematic. However, the opposite case is much more problematic. So if you have a malignant tumor but you classify as benign, then you will not treat it maybe as urgently as you should, and the lack of treatments might lead to the death of the patient. So the cost of the first type of misclassification is much less than the type of the second type of misclassification, because the latter might lead to death, whereas the former might lead to some few additional tests, which would cost some money, but is much less tragic than dying. So here in this example, the second type of misclassification is much more costly. So often when we do classification, we like to reflect this in our analysis. So it's not necessarily only the error rate that counts, but it's the cost, ultimately misclassification cost, that can be more important. So to reflect this in practice, you could introduce what we call a loss function. So a loss function is a function L which has two inputs. So the two inputs are two classes and returns a loss or some form of cost between 0 and infinity, where LG1, G2 denotes the cost of classifying an observation which is truly in class G2, of classifying an observation where the true class of that observation is G1, but where you classify it into class G2. So, for example, if you classify a blue observation into orange, then G1 would be blue, and then G2 would be orange. So for these loss functions, we set LGG is equal to 0. So when you correctly classify an observation, typically there's no cost, or well, you could have something different, but there's no point in adding cost in that case. And conversely, when G1 is different than G2, you assign a positive cost, because you want to penalize these types of misclassifications. And the idea here is introducing this loss function allows to consider different costs for the different types of misclassification. Okay, so for example, LG1, G2 could be different than LG2, G1. So in that case, we have asymmetric costs, and therefore your model will penalize much more misclassifications that are more costly. Okay, so how to use this loss function within a classifier? Then the idea here is to replace our objective function by, instead of minimizing the probability of a classification error, we will minimize the expected value of the misclassification cost. Okay, so here, if we have a new observation x0, and we like to classify this new observation so as to determine its class g0, what we could do instead is to select g0 hat as the class which would minimize the expected cost of misclassification given the current value of predictors. So here, G0 is the true class of the observation, and the small g is the class into which we're going to classify the observation. Okay, so instead of to minimize the probability of classification error, we could use an alternative criterion, which is to minimize the expected misclassification loss. Okay, and this expression, this expected loss, it can be simply represented as the sum across all types of misclassifications of the misclassification's cost times the probability of having each respective types of misclassification. Okay, so if you know the conditional probabilities of all types of misclassifications, then it's really easy to express this as the sum of weighted costs for each type of misclassification times their respective probabilities of such cost. Okay, so from that, because these depend on conditional probabilities of misclassifications, we need to estimate the conditional probabilities of being in each class given the predictors, and this is exactly what we've done earlier. Okay, so to estimate the probabilities of being in each class given your predictors, you can still use the same exact methods we've considered earlier. You can consider k-nearest neighbors, linear discriminant analysis, quadratic discriminant analysis, logistic regression. So all these methods still apply here to determine the probabilities of being in each class. But then it's just at the end, once you have these probabilities of being in each class, how you perform your classification. Instead of just looking at the probabilities of errors, you look at these probabilities now, but weighted by the cost of each type of misclassification. So how does it compare with our original approach? Well, we see that if we use a loss function which is 0 for all class LGG is equal to 0 for all classes G. So here this was our assumption that correct classification entails no misclassification cost. But if you use a loss associated to any type of misclassification equal to 1. So whenever G1 is different than G2, you assume that LG1, G2 is equal to 1. This will entail that all types of misclassifications have an equal penalty of 1, and therefore your expected loss of classification given your predictors, because this loss is 1 whenever, if and only if G1 is different than G2, then this expectation simply becomes the probability that the true class is different than the estimated one. So this goes back to our original approach of minimizing the probability of misclassification, and therefore in that case the expected loss would just be the base classifier error. Okay, so you fall back on the original minimization of the classification error we've outlined. Okay, so we'll stop the lecture here, and in the next lecture we'll discuss some additional diagnostic tools to determine the accuracy of classification models for binary classification problems. So thanks for listening. I'll see you next time.